Hello everyone, welcome back to ECE350, lecture number 2. Today we're going to talk about traveling wave in a lossy media, and also we're going to talk about complex number in review. Also we're going to talk about some tech brief. So loss media means in the last class we talked about lossless media, right? Your amplitude is not changing when it's traveling through the media, but in lossy media, your amplitude is changing. So look at that. Here is a 10 meter amplitude, and it's changing over here and slowly going down, right? So this one is following this equation over here. So this is the exponential decay right here, right? This is the attenuation factor, alpha. So that is the attenuation factor alpha, making it attenuate. So for lossless media, alpha is 0. For lossy media, alpha is not 0. It's a non-zero value. So that's why your waveform is going down when it's going through the media. So we're gonna do some simulation in the class. So also going to do this problem in the class. I'm going to skip the problem. So we're going to do that problem. A spectra, depending on the wavelength, it's a different spectra does for different work. Like for this whole thing over here, we use them for communications. And we have a very small wavelength is visible, and the infrared on here, ultraviolet over here, and gamma ray on other things over here for the cancer treatment and other medical treatment. This is the United States, how they basically divided the frequency for different applications. That's right here. It's very hard to read, but that's what is United States allocate frequency for different applications. Tag brief one. So for the light, we have three different options, right? We have a older style incandescent light, and we have a fluorescent light, and we have LED light. What are they? For this one over here, for your incandescent light, it's basically a filament, tungsten filament. When the current goes through it, it heats up and emits light. So that light is very pleasant for the eye, but it's very inefficient. And for the fluorescence over here, what happened when you apply the electricity, there is some circuit over here to make from your AC to DC kind of thing. Then you have a two electrode. So between two electrode, your electron is jumping from one electrode to another. They're not connected, so the electron is jumping from one electrode to another electrode. And this tube is full of gases like mercury or any other let's say noble gases like argon, neon, and xenon. So when your electron going from one electrode to another electrode, that's basically charges this neutral gas and let them emit their own, free their own electrons. So those electrons goes to the higher energy level, and when from higher energy level to comes to the ground level, so those electrons basically emits light. That's how we see light from this fluorescence. And then LED. LED is another technology. Going to go back here. So LED, when you apply, it's a semiconductor. It's a PN junction. You all know that. So when you apply electricity to LEDs, that when hole and the electron combines, is emits photon. That's what you see the lights coming out of the LED, right? So that photons, that's what you see when holes and electron combines in the semiconductor. So in semiconductor, all of them over here. So we have let's say moonlight. This is over here. Then this comes from the older style incandescent light bulb, and this one is coming from the fluorescent light bulb, and this one is coming from the white LED. Let's talk about the white LED here. You can make a white LED by combining all three color, red, blue, and green. But it's very expensive to have three different LEDs combining in one and make it white. But in reality, we do it all phosphorus-based blue LED. So we have blue LED emits blue light, and on the outside of the what do you call it, LED encapsulate, we have phosphorus powder particles there. So then your phosphorus powder particles absorb light from the blue LED and re-emit that as a white LED. That's why it's called white LED with phosphorus-based blue. That's the very economical solution to make white LED out of blue LED. So If you compare them, you can see that luminous efficacy, incandescent is lumens per watt is only 12, fluorescent is 40, and look at this, these are very high, right? So then useful lifetime, also this is a high one here, but doesn't also have the high cost, initial cost over here. But over the years, this has the lowest cost compared to incandescents or also fluorescents. So now I assume that all the household has most LED light than anything else. Another application for electromagnetic field is LCD, liquid crystal display. Most of the thing we have around us had some kind of LCD or OLED. We're not gonna get to the OLED here now. We're gonna get to them later on. How is LCD works? You have a filter over here. When incoming light, you're filtering filter out the horizontal component. Only have the vertical component over here. Then it goes through. This is the LCD over here. It goes through LCD in between right here. So this LCD materials over here, liquid crystal over here, if you don't supply any voltage for the liquid crystal, it's going to twist your light coming in. If you supply a voltage, these materials will straighten out, and it's not going to twist your light. So over here, this one and this one has a voltage supply, enough voltage supply, so it straighten the material. There's no twisting happening. But over here, for this one, there's no light voltage supply here, and also this one, no voltage supply here. Both are twisted, right? So twisted means now if you have another filter which is horizontal filter, so all these things not twisted will block. The twisted one will go through it. Then if you go through the display over here, right, and it's gonna show up as a bright spot. If you look at the other side, you will see 3 as a dark one because you brighten the other 2 by using LCD. So you can control them as you want, very small portion of LCD to make your display as precise, as concentrated as you want. And same thing we're showing over here, same thing here, and this is the description of what I said. Now let's go to complex number. Complex number, yeah, as you know that this is complex number over here, and then J is basically your I, if you remember from your math courses. So that is complex notation there. And so real is X, imagine is Y. And if you combine them, you can use this format here. Also, any other format you might remember from your previous class. And this is the Euler identity, right? So all format comes to the same thing here. So if I use this one, bring it over here, and so on. So, and they had a nice chart over here about the complex number. I'm not going to spend more time here. Complex number basically given a tool to solve some circuit problem or any other electromagnetic fields problem very easily. That's all for this one. We're going to see you for lecture 3.